Hello friends, welcome to my channel. My name is Samrit Shetty and I am a student at Sardar Patel Institute of Technology, Andheri. My friends and I, Atharva Khode and Uday Yeshi, are about to deliver a presentation on function generator and arbitrary function generator. So let's begin. The contents of this presentation would include the introduction of both the equipment as well as their working principles and the differences. Introduction. So, what is a function generator and arbitrary function generator? Function generator and its counterpart, the arbitrary function generator, happen to be some of the most important pieces of technology used by engineers, especially in our field. Function generators help us to generate different types of electrical waveforms, such as square waveforms, triangular waveforms, or sine waveforms. Function generators find extensive use in electronics for testing, calibration, and educational purposes due to their ability to produce controlled and precise electrical signals. Moving on, the working principle of function generators. A function generator operates by using an oscillator circuit to produce basic waveforms like sine, square, or triangular ones. Users control parameters such as frequency and amplitude to the device's interface, allowing for versatile signal generation in electronic testing and experimentation. The generated waveform passes through shaping circuits and an output buffer, providing a controlled output for various applications. The function generator includes equipment such as oscillator circuit, frequency control, and waveform shaping, amplitude control, output buffer, and user interface. Oscillator circuit. It is the core component that generates a basic waveform, usually a sine wave. Frequency control adjusts the rate at which the oscillator produces the waveform controlled by the user. Waveform shaping modifies the sine wave to create different waveforms like sine waves or square waves or triangular waves. Amplitude control. An amplitude control feature enables users to adjust the magnitude or voltage level of the generated waveform. Output buffer. The generated waveform passes through an output buffer, ensuring it has sufficient current capability to drive external loads. User interface. Equipped with user controls, the interface allows easy adjustment of parameters like frequency and amplitude for waveform customization. So, moving on to the applications of a function generator. Function generators are used in a wide variety of fields. They are used for waveform generation, amplitude testing, frequency testing, and modulation. Waveform generation. The primary function of a function generator is to produce different types of electrical waveforms, such as sine waves, triangular waves, square waves, sawtooth waves, and more. Amplitude testing. Engineers use function generator to test the amplitude response of devices. This is important for studying and understanding how a circuit responds to different signal amplitudes. Frequency testing. Function generators are used to test the frequency response of electrical components and circuits. Engineers can input specific frequencies and observe how a circuit or component responds. Modulation. Function generators are often equipped with modulation capabilities. Amplitude modulation, frequency modulation, and phase modulation can be applied to the generated waveforms. This is useful for simulating real-world signal conditions. Now, on to the differences between the function generator and the arbitrary function generator. The function generator provides predefined waveforms, meaning it generates standard waveforms like sine, square, triangle, and sawtooth. The arbitrary generator, on the other hand, provides customizable waveforms, meaning it can generate user-defined waveforms, allowing for greater waveform flexibility and complexity. The function generator has limited flexibility, which means that it is only limited to predefined waveforms and specific modulation options, whereas the arbitrary function generator, on the other hand, provides extensive flexibility in waveform creation, modulation, manipulation. The function generator has just typical applications, which is commonly used for general purpose testing, educational purposes, and basic waveform generation. The arbitrary function generator, on the other hand, is ideal for applications requiring specific non-standard waveforms such as telecommunications, signal processing, and advanced search. And finally, the cost of the two function generators. The function generator is generally more cost effective compared to arbitrary function generator, whereas the arbitrary function generator is usually more expensive. Moving on to the block diagram. This is the block diagram of a function generator. A constant current is supplied to the integrator by current supply source 1. Due to this, the voltage of the integrator rises linearly with respect to time. This linear rise is according to the output signal voltage equation. Any increase or decrease in the current will resultantly increase or decrease the slope of the voltage at the output and thus controls the frequency. The voltage comparator multivibrator present here caused by variation in the state of the integrator output voltage at a previously determined maximum level. Due to this change of state, the current supply from source 1 cuts off and switches to supply source 2. A reverse current is supplied to the integrator by current source 2. This reverse current causes drop in the output of integrator linearly with time. As before this, time also, when the output attains a predetermined level, the comparator again changes its state and switches to current supply source 1. Thus, we will have a triangular wave at the output of the integrator whose frequency depends on the current by the supply sources, as we can see in the block diagram shown. A square wave signal is obtained at the output of the comparator. The resistance diode network employed in the circuit changes the slope of the triangular wave with distortion less than 1%. The output amplifier thus helps to provide two waves at the output simultaneously. This captured signal can be displayed by using an oscilloscope.
Good morning guys, we are from SPIT college and here we are present in this lab to perform this experiment which is based on function generator, and here there is an internal circuit diagram of this function generator. As we can see here, there is a block diagram, and this is a practical function generator which was manufactured by Applab company. It is a 3 MHz multi-waveform serial generator and its model number is MSG3M. This function generator supports maximum 3 MHz of frequency. Basically, the function generator is used to generate various types of signals like sine wave, square wave and triangular wave of various frequency, as well as we can change its amplitude according to our requirement. So here there is knobs, total 1, 2, 3, 4, 5 knobs are there, and here there is switches to change the frequency range, and here there is switches to change the type of function. Basically in this practical we have connected the output of function generator to DSO, which is our digital storage oscilloscope. And basically here we are using DSO to see the visual representation of the output which is generated by this function generator. So from here my friend will take over.
So thank you Atharva for taking me. First, this is the basically it is the front panel of the function generator. Here is the display at which frequency or amplitude, so we can adjust the amplitude and the frequency as per our requirement. So first here is the frequency and amplitude switch. So from here we can see the amplitude of the output signal, and here is the frequency of the output signal. Here is the three lines indicating that the frequency is in the hertz, kilohertz or the megahertz. So coarse and the fine, both knobs are used to control the frequency at the output signal. So here are the various frequency knob which is the minimum frequency is 0.3 hertz to 3 megahertz. So it is 3 megahertz is the highest frequency of the function generator. So second part is the symmetry switch. From the symmetry switch we can symmetrical at the output signal, we can make the signal as a symmetrical. So both the input, both the positive half and negative half can be symmetrical to each other. So this is the DC offset knob. From this we can change the offset of the output signal, and we can make it positive or make it negative also. So this is the attenuation knob which can attenuate our signal at the output, and here is the TTL which is used. The TTL is the transistor logic. From here we first get the frequency and the output. So make the frequency knob at the any type of frequency range. So I took it here, and after this it is selected on the sine wave. So from this auto set button, so we can see the output as a sine wave. After this we can shift it to the triangular wave, or similarly with the square wave. So By the symmetry now we can say the both are symmetrical and take it off. So here is the offset knob. So as we make the offset at positive volt, so as you can see the voltage, the our sine wave is goes upward, and as we make it negative, so it goes the downward. So make it at the center, and here is the attenuation knob. So
Moving on to the arbitrary function generator's block diagram. It has always been a significant design challenge to create stimulus signals that can fully exercise a prototype. In the case of RF applications, complex, high-frequency modulated signals with jitter, spread spectrum clocking, and other time-variant effects have traditionally required a benchtop of pulse, function, modulation, and RF generators. While MATLAB and signal processing toolbox are common for signal generation, AFGs now feature a plugin architecture for easier waveform creation. These plugins, integrated into the AFG's GUI or run on a PC, accelerate the process of generating signals for specific applications or simulating real-world environments. Plugins cover areas such as generic precompensation, high-speed serial, multitone and chirp, and optical signals. Some common plugin capabilities include generic precompensation, simple generation correction features for cleaner signals and lower error vector magnitudes. Users can compensate for Nyquist zones, define LO frequency, and specify bandwidth. High-speed serial facilitates signal creation and jitter simulations for design validation. Margin characterization and conformance testing. Capabilities include jitter generation, spread spectrum clocking, pre-emphasis, and noise addition. Multitone and chirp, useful for military, aerospace, and RF applications, allowing the creation of tones and chirps with specified frequency and characteristics. Optical simplifies the creation of modulated optical signals for high-speed telecommunication networks supporting various modulation formats.
hello everyone. As you know, the second part of our experiment is arbitrary function generator. So I am excited to share with you a hands-on experiment featuring an arbitrary function generator. We will explore its front panel, understanding its functionalities, and demonstrate various waveform types. So firstly, let's take a closer look at the front panel of our arbitrary function generator. This, as you can see, the manufacturer of this arbitrary function generator is Tektronix, and the model number is AFGS1002. So for the practical demonstration, I will connect the arbitrary function generator to an 4-channel digital oscilloscope. So as you can see the generator waveform in real time. This visual representation will help you better understand how the settings on the front panel is equipped with various controller and settings. We have frequency adjustment, amplitude controls, waveform selections, and more. So understanding these features is crucial for tailoring the output to our specific needs. So now let's dive into the practical aspect. I will demonstrate different waveforms types that this generator can produce. We will explore sine waves, square waves, triangular waves, and maybe even some more complex waveform. Each waveform has unique characteristics suitable for different scenarios. So I will also touch on the practical applications of each waveform. Sine waves are often used in audio applications, square waves in digital circuits, and triangular waves in certain testing scenarios. Knowing when to use each waveform is key to maximizing the potential of your arbitrary function generator. This visual representation will help you better understand how the settings on the front panel impact the output. So okay, then this after there is a arbitrary waveform, means this signal can be varied according to our need. So this signal can be is not a sine wave, square wave, or triangular wave. It can be is a user desired signal can be used. So here is the signal like use structure. So